Hi everyone, this is BKEP from the Baker Lab. We just rolled out a new update for the hydrogen bond network filter, and I wanted to take some time and look at some hydrogen bond networks with you. Um, so here we have a structure that was designed in the Baker Lab, mostly. A lot of the side chains have been trimmed down to alanines, but it has a hydrogen bond network in the middle that I think is exemplary and a good example to look at for an ideal hydrogen bond network. So the first thing I want to do is uh, visualize the hydrogen bond network. And we do that just by going to this the conditions tab on any puzzle that has a hydrogen bond network filter. Click show, and now we see that there's a hydrogen bond network here. We can mouse over it to see some statistics about it, the percentage of polar atoms that are satisfied, the number of interface H bonds. Those are H bonds that span from one monomer unit to another, um, and then the total score you get for that network. Additionally, you can mouse over this conditions up here and see some more about the filter in general. So in this case, just a puzzle I threw together, this network must have at least 3 H bonds, one interface H bond, and satisfy at least 0% polars. So this is unrealistic. We generally want to satisfy a bunch of polars, as many as possible. But this is a hydrogen bond network that I want to look at a little bit more closely. So the next thing we want to do is make sure that we have advanced GUI options enabled. And then we'll go to our view options, and I want to make sure I can see all the side chains. And I like to color the atoms with CPK coloring so I can see which atoms are red, those are oxygens, and which ones are blue, those are nitrogens. And here we see that, that hydrogen bonds are typically forming between red atoms and blue atoms, which is typical for reasons we'll get to in a minute. But again, looking at the statistics for this network, we see that only 75% of the polar atoms are satisfied, whereas at first glance it appears that all of the polar atoms are satisfied. Um, Looking at just this symmetric unit, we have 1, 2, 3, 4, 5 oxygen and nitrogens, and they're all making at least one hydrogen bond. But we need to dig a little bit deeper. And the best way to do that is in the view options to look at something with polar H's. So line polar H, or I like stick polar H. Now, if we zoom in a little bit, we can see that these blue atoms have 2 hydrogen atoms bonded to them, which is typical. Nitrogen tends to be bonded to hydrogen atoms, whereas oxygen often has lone pairs. And that's what makes nitrogen often a hydrogen bond donor. It donates a hydrogen to this hydrogen bond, and oxygen an acceptor. So this oxygen is accepting this hydrogen from this nitrogen here. And that's the nature, that's kind of the essence of a hydrogen bond, is just the sharing of this hydrogen between its donor and its acceptor. And now if we look at this network, we see that there are 1, 2, 3 polar atoms, or 3 hydrogen bonding atoms on this residue. There are 1, 2, 3 hydrogen bonding atoms on this residue, and there are actually 2 on the serine over here. You notice that serine actually can accept a hydrogen bond with this oxygen and can also donate a hydrogen bond with the hydrogen that's connected to that oxygen. And this hydrogen and this hydrogen, 2 of these atoms are not making hydrogen bonds. So that is why this hydrogen bond network is only 75% satisfied. Of course, you would get the same thing if you looked at the symmetric copies. And we see that we are getting, there are 6 hydrogen bonds that span an interface. There's 1 here, 1 here, 1 here, 1 here, and then 1 here and 1 here. So there are 2 for each interface, and you have the symmetric copies. So you have 6 total. The score is calculated from the number of interface hydrogen bonds times the percent satisfied, and then times some scaling factor, which I think here is 100. So what you get is 6 times 75% times 100, and you have 44 points for this hydrogen bond network. So what this means is that to get a lot of points, what you want is you want a network that is very satisfied. You want one that is 100% satisfied, and you want to have the maximum number of interface H bonds that are allowed for that puzzle. So this is an ideal hydrogen bond network. This is what we would like Foldit players to strive for, or to even to beat. If you could satisfy even these other polar atoms, which realistically would make hydrogen bonds with water probably, or at least this serine would. But in terms of Foldit, we count only hydrogen bonds with the protein, not with water. Yes, so this is another thing you might realize here is that this hydrogen bond network is isolated to just one part of the protein. This is actually a very large protein. I'm going to go back to cartoon mode. So there are 6 helices in this protein, and only this one hydrogen bond network on this end. And that's really all you need, just 1 or 2 of these hydrogen bond networks sprinkled amongst an otherwise very hydrophobic interface will give us exactly what we want, which is improved solubility of this protein in water, and also improved specificity, so that this protein, instead of binding just anything hydrophobic that it encounters, it will only bind to other proteins that can satisfy these hydrogen bonds right here. And that's very important. So let's look at some Foldit structures. These are Foldit structures from Foldit designs from puzzle 1150, I think. Puzzle 1150 was a dimer 60 residue, is that right? I think it was, yeah, a 60 residue symmetric dimer design puzzle with a hydrogen bond network filter, and I want to look at a couple Foldit designs. So this is a shared solution, actually. This is one that a player shared with scientists that I really like, and so I wanna look at it and talk about what I really like. So first, we see that there are several hydrogen bond networks here. We have 1, 2, 3, 4 networks in total, and they have some different statistics. It looks like this network here is a symmetric copy of this network back here, and this network is a symmetric copy of this this other network down here. So we have 2 unique hydrogen bond networks, each of which has a symmetric pair. And I want to point out that previously, in the way we had been calculating this, I think only one of these symmetric copies would have counted. That is no longer the case. All of these hydrogen bond networks are treated individually by Foldit now. So they will be scored each as its own hydrogen bond network. So if we go up to this hydrogen bond filter and hover over, we see that in this puzzle, this network must have at least 3 hydrogen bonds, 1 interface bond, and satisfy at least 75% polars. And here we can get credit for up to 4 interface bonds, and I changed that from the original puzzle just to demonstrate how this actually plays out. So let's see what we have here. This big network right here is only 58% satisfied, and it only makes 1 interface H bond. Because it's only 58% satisfied, we won't get any points for this network. It's not even considered by Foldit for a bonus. So this is something that a player would have to work to improve. It would have to make sure that more of these atoms form hydrogen bonds. And so I see an oxygen here that's not making any. This nitrogen here probably needs to make 2. Similarly, these nitrogens need to make 2 hydrogen bonds each, and also these up here need to make some additional hydrogen bonds. So this network is not getting any points, and neither is its symmetric copy down here. This other network over here looks much better. It is 80% satisfied, and it is making 3 interface hydrogen bonds. So what that means is that for this, oops, I did not want to pull. Here we have 3 interface H bonds times 80%, and then times the scaling factor, which I think here is 100 again. So this hydrogen bond network gets 240 points. If we look at its symmetric copy, we'll spin the protein around. If we look at its symmetric copy, we see that this network is only credited with 1 interface H bond. Even though it makes 3 interface H bonds, it is only getting credit for 1 of those, and that's why it only scores 80 points. And the reason for that is, remember, if we looked up at the network filter, you will only get credit for up to 4 interface bonds. So what Foldit will do is it will go through and find all of your networks, and then it will start assigning points starting with the most satisfied network. So if you have a network that's getting 100% satisfied and then another network that's only 77% satisfied, Foldit will make sure that you're getting credit for the H bonds in the 100% satisfied network. But yeah, so what we want to emphasize here is that we don't need to have huge extensive networks all over the protein. We just want to have a few hydrogen bonds that span the interface and that are backed up with a 100% satisfied network. So if we look at this 80% satisfied network looks really good to me. It's this buried tryptophan. Let's look at this one down here, the symmetric copy. This buried tryptophan is very nice. It has a lot of tryptophan is mostly hydrophobic, which is good. It'll make for a strong interface. And this one polar atom on tryptophan is satisfied by this glutamate up here. And likewise, the glutamate is satisfied by an arginine on the opposing symmetric unit, which is also backed up by another what is that, aspartate right here. So what you get is you get this nice hydrogen bonding across the interface, as well as this large hydrophobic group that packs really well at the interface. So this confers strength to the interface, and this confers specificity. And this is really cool. We don't see a lot of hydrogen bond networks in the Baker lab with tryptophans, and I really like this one. I'll also point out that it looks like there's another potential hydrogen bond network right here. You know, maybe this tyrosine is just out of range of this glutamate and this tryptophan. But you can imagine that would be another great place for a hydrogen bond network. In fact, let's see, what does that look like? Oh, yes, and in fact, excuse me, it does. It does form a hydrogen bond network, but it's only 2 hydrogen bonds big. This network would only include 2 hydrogen bonds. And remember, this filter requires that a network have at least 3 hydrogen bonds. And that's just to make sure that these hydrogen bond networks are highly connected and really integral to the protein's construction. So actually, this is an extra bonus here. You know, I almost wish that the hydrogen bond network would recognize this network in this case and award it some points, because this is also a very nice interaction. You have a large, mostly hydrophobic residue that is completely satisfied in making specific hydrogen bonds across the interface. So that's really nice. The only tiny problem that I have with this structure is that I think there's a bit of a void in the middle. I think there's some empty space. Ooh, it doesn't even show up in voids. It's too bad. But this the center of this protein looks a little bit underpacked to me, and it's not too bad. This is a design that I'm really interested in, and will very likely follow up on. We will push this through our pipeline. but this is a really great design. Has lots of nice hydrophobic packing in the core with also these hydrogen bonds at the interface backed up by satisfied networks. So this is a model design. I'm really happy to see this from Foldit players, and would really like to see more. Looking at a couple others, these are some. These next two are top scoring structures from the same puzzle, puzzle 1150, that are not so great for a couple of reasons. So this one has a couple hydrogen bond networks here that are both at least 77% satisfied, and will satisfy the filter and get some bonus points for it. The problem I have with these is that they're only at the surface. The entire core of this protein is non-polar, is completely hydrophobic. So we don't have we probably wouldn't improve the solubility of these monomer units much because it still has this really massive hydrophobic face. Each monomer has a really massive hydrophobic face that would bind to anything it encounters, anything hydrophobic it encounters, not just its symmetric partner. And likewise, these residues, which are at the surface, would likely already be able to make hydrogen bonds with water. So they don't get much bonus from making hydrogen bonds with themselves instead. So this interaction doesn't really contribute any strength to the interface, and very little, if any, specificity. There's maybe some charge complementarity, this positively charged residue with these two negative ones. But for the most part, these hydrogen bond networks are physically not contributing very much. The other thing that is really a bigger issue with this design that is more difficult to see and is not really visualized well in Foldit is that this tryptophan here has a polar atom that is completely buried. So you see that solvent, water, would have no way to get to this polar atom and make a hydrogen bond to it, which is really unfavorable. Very rarely do you find this in natural structures where you have a buried polar atom that does not make a hydrogen bond. So that would actually probably prohibit these proteins from binding one another, or at least from binding very strongly. So that's another problem. And hopefully that tryptophan is not scoring too great. I imagine it's there because it packs really well. It has the perfect shape to kind of fill that spot. And that is one strength of this design, is that interface looks very interdigitated and well packed. So otherwise a very good looking design, but unfortunately the hydrogen bond networks here are not what we're looking for. If we look at another one, we have kind of the opposite case. So this one is littered with hydrogen bonds. Hydrogen bonds all over the place. Someone is very good, very adept at making hydrogen bond networks. And we see that these ones in the middle are completely 100% satisfied, which is cool. That's very cool. We like to see that. So those hydrogen bonds, each one individually, is actually probably not bad. And the geometry of these is a little questionable, but it could happen actually. Those serines could form the hydrogen bonds that we've designed here. The problem here is that this interface is completely hydrophilic. There are no nonpolar residues. There's a cysteine right here, which is the closest we're going to get to a nonpolar residue in this design. Even in the core of the monomer, it's dominated by these serines. So this is not so good. In fact, these serines don't even, or maybe they do make hydrogen bonds, but you don't want polar cores in your monomer unit. You definitely don't want polar cores in your monomer unit. Again, it's okay to have a few satisfied hydrogen bonding molecules or residues at the interface, and that's the point of our hydrogen bond network filter, is to reduce kind of the overwhelming non-polar interfaces that we have been seeing. But we still will need to retain some hydrophobics to make for a strong interface and leave just one or two networks in here to confer that specificity that we're looking for. Um, so this is again, this is not something that we're terribly interested in. Maybe if we could design away a couple of these hydrogen bond networks with some nonpolar hydrophobic residues, we could improve this design a lot. Um, and the other thing here, you see that there are a lot of hydrogen bond networks on the outside of this protein. These aren't satisfied so much. Um, but those, again, these don't contribute very much, if anything, to stability, um, because these residues can just as easily make hydrogen bonds with water and be perfectly satisfied. Um, so hydrogen bond networks, again, hydrogen bond networks on the surface of the protein do not contribute um, at all to stability, or especially to binding at the interface. And the last structure I want to look at is another shared with scientists solution that I just think is really cool. This is this is dessert for me. This is what I love to see after a fold-it puzzle is something. What a crazy fold! So it looks like we have four stranded beta sheet backed up by two helices, and then the same thing on the other side, and they're kind of domain swapped. So they're extended. This is a really cool fold. Maybe probably unlikely to fold up, but this type of thing really showcases the ingenuity of folded players, and I think this is something that is really cool. It would be very cool if it folds up, and it might be worth trying with some refinement. But I really like the fold of it, and it actually does some cool things with the hydrogen bond networks as well. So if we zoom in here, let's see, there's a histidine hiding back here that I want to focus on. So yes, so here we have that's not what I want. Let's see. Here we have a histidine making a hydrogen bond with this, it looks like an aspartate. I'm sorry, I'm having trouble navigating this protein here. So it's making a hydrogen bond actually with this threonine, which is backed up by an aspartate, and looks like a glutamate and an arginine. And one of the things I want to look at is actually the hydrogen bonds on this histidine. So we see that this histidine actually has two nitrogen atoms, two blue atoms. One of them has a hydrogen, and the other, on the other side, does not. Tough to see. Yeah, so this side does not have a hydrogen, and that is typical of histidine at physiological pH. The cool thing about histidine, and what makes it very interesting to biochemists and protein design in particular, is that it has a pKa of close to physiological pH. So at about pH 6, this nitrogen here will acquire another proton and another hydrogen here. So this histidine will actually have two hydrogens instead of just this one. And the reason that's interesting for protein design is because this nitrogen, which here is accepting a hydrogen bond from this threonine, after it's protonated, once the pH drops to 6 or below, and it's protonated, it will no longer be able to make this hydrogen bond with this threonine. And any benefit that it's gaining from this hydrogen bond will disappear. And so what you can imagine is building a hydrogen bond network that includes histidines, so that you have a nice, strong, and specific interface between two monomer units, and then dropping the pH to some level such that these histidines become protonated with a hydrogen, and then suddenly the interface would fall apart because those hydrogen bonds would not be able to be satisfied anymore, and the protein would fall apart. It would fail to make the complex, which is very cool. There you have something. You have a pH. Uh, if you have a histidine mediated hydrogen bond network, then you could have a pH responsive binding event, which is very cool. That would be immensely useful in tons and tons of applications. But is again is difficult to design. In fact, again, very few Baker Lab designs are able to incorporate histidines into their hydrogen bond networks. Um, so that's also a very cool thing about this design. These networks are, well, this one is 77% satisfied, so that's nice. Um, a lot of these other hydrogen bonds are not so great, um, or at least just short of contributing to a network. So you might want to improve the geometry. It looks like this hydrogen, for example, is not pointed directly at the acceptor unit, um, which is generally what you want in a hydrogen bond. But anyways, these hydrogen bond networks that Foldit players are sending us are very, very cool. I know the tools have been kind of cryptic and difficult to manage up to now, and I appreciate everyone, all of your hard work and keeping with us while we kind of work through this and figure out how to incorporate um, hydrogen bond networks into Foldit designs. But I think we're getting very, very close, and I'm very excited uh, to see what Foldit players come up with next. Um, so yes, thank you to all the Foldit players who have played these puzzles and have designed these wonderful proteins. And good luck in the future. Happy folding.